Hello everyone, this is Zhihang Sun from Tsinghua University. I'm glad to present our recent work in concurrent program verification. The title is Consistency Preserving Propagation for SMT Solving of Concurrent Program Verification. The verification of concurrent programs is complicated because of the vast number of thread interleaving. Consider this example with two child threads. Both threads are short, but it's hard to enumerate all possible executions. Note that some statements not necessarily happen. Depending on branch conditions, we call them guard conditions. Here we only list two possible executions where the assertion holds, but there are much more. This is why concurrent program verification is difficult. An efficient way to verify concurrent programs is to use partial orders. One can model and analyze the execution order of memory access events to represent possible program executions. Events are sorted into read and write events, R and W in the picture. Consider the example program in concurrent SSA form and memory model SC, TSO, and PSO. Some orders, called preserved program orders, are fixed based on the program and the memory model. Note that choices of memory models only influence these preserved program orders, but parallel to our proposed method. An important and special partial order is the read-from order. It links a write event to a read event to represent that the read event obtains its value from the write event. For each possible read-from order, we define a read-from variable. For example, x2 can read from either x1 or x3. We define variables rf12x and rf32x. rf12x is true, represents that x2 really reads from x1. Note that a read event can only read from the latest write event to the same address. In the following circumstance, x2 reads from x1, but x3 happens between them, so x2 should read from x3 instead. Therefore, this circumstance is invalid. We build axioms to eliminate such invalid situations. Now we introduce our ordering consistency theory. It consists of events and orders between events. Among those orders, read-from orders are specifically labeled. A set of orders represents an execution, is consistent if and only if there is no self-loop. Given a program with a safety property, we aim to find an execution consistent and property violating, or prove that no such execution exists. So we only care about consistent executions. When we find a self-loop, we treat it as an inconsistency and try to resolve it. The first axiom, transitivity, because the orders are partial. The second axiom, if R reads from W1, but some W2 precedes R, W2 must also precede W1. The third axiom, if R reads from W1 and some W2 happens after W1, W2 must also happen after R. The last two axioms guarantee that when R reads from W1, no W2 happens between them. Now, from the theory definition and axioms, there is a traditional design of a basic theory solver. Once an assignment is made, theory propagation uses axioms to derive orders as many as possible. After theory propagation derives all orders, consistency checking finds self-loops among these orders. If a self-loop is found, we call this an inconsistency and generate the corresponding conflict clause. However, our main contribution lies in an improvement of the theory solver. We propose preventive reasoning to prevent in advance self-loops from occurring, so that orders are always consistent, no more need for checkings and conflict clauses. The main idea is that if an unassigned literal will lead to self-loop upon assignment, we call this a fragile literal and make the offset assignment to prevent the self-loop. We have found and proved that each self-loop can be attributed to either of the two following patterns. The first pattern violates read-from semantics. This consists of two normal orders, one read-from order and a guard. When all but one are satisfied, we make the last one not satisfied. The second pattern is more direct and simple, one normal edge and one read-from edge. Our action is similar and simpler. When one is satisfied, we make the other not satisfied. Well, the idea is rather simple, but we spend much effort on designing algorithms for preventive reasoning soundness and completeness, and proving it really preserves consistency, so that no more consistency checking and conflict clauses needed. We implement our approach on top of CBMC and Miniset. Our tool is called DIGO. Under Memory Model SC, we compare DIGO on SVCOM 2022 benchmarks with several state-of-the-art concurrent verification tools. CBMC, the basis of all partial order approaches. RORD, our previous partial order work published in PLDI 2021. Lazy CSEQ, another approach based on sequentialization. Yoga CBMC, a novel approach that uses partial order in an abstract refinement manner. Under weak memory models TSO and PSO, since Yoga CBMC is the only baseline that supports them, we also compare DIGO with Yoga CBMC. DIGO solves more cases than these tools. Counting on both solved cases, DIGO significantly improves solving efficiency and consumes less memory. To evaluate preventive reasoning's efficiency gains, we also implement a version without preventive reasoning called DIGO-. Results on these two versions show efficiency of preventive reasoning. In detail, preventive reasoning reduces the number of decisions and propagations in the SMT solving procedure. As a conclusion, our contribution includes a sound and complete preventive reasoning method on ordering consistency series, a consistency-preserving series solver based on this method, and outperforming in state-of-the-art concurrency verifiers in SVCOM 2022 benchmarks. That's all. Thanks for your listening. Any questions?
I would like to ask the authors of the consistent preserving propagation for SMT solving of concurrent program verification. You have shown a couple of axioms, and I wanted to, in your talk, I wanted to ask what motivates those axioms. Is it the particular architecture that you are interested, that you are working on? So, Zhuhang, you are on stage.
Well, do you mean memory models?
Yes.
Now we work on SC, the commonly only assumed architecture, and TSO, PSO. These weak memory models, TSO and PSO, are commonly used in some hardware, real-world hardware architectures.
Right. So, do these memory models motivate why the axioms make sense?
Well, we have mentioned that our proposed approach is parallel or orthogonal to the choice of memory models. Those memory models only influence the program order. Yes, what program order should be retained or relaxed.
Right. So your tool uses the axioms. Class is parameterized with a memory model in order to decide what order of executions are possible.
Yes, exactly.
Right. So then what motivates the axioms? Why are the axioms sensible? Perhaps you can also show the slide.
Yes. This is the read from semantics. a read event can read from a write event only if this write event is not overwritten. So if read event R reads from write event W1, then no W2 should happen after W1 and before R. This is easy principle to follow, and we haven't considered what motivates this.
You mean it's obvious what motivates it?
Yes, it's somewhat obvious.
Okay, right. Okay. Can your technique be used to demonstrate that there are no data races?
Data analysis.
No, data races.
Data races. Yes, this is exactly our future work. We are now working on this and will publish something perhaps next year. Now,
right.
Data race means that two events happens exactly at the same time. So if event E1 data races with E2, neither E happens before E2 nor E2 happens before E1. This is not our idea.
Sorry, are you saying that you represent data races as a cycle in the event dependencies?
Well, data dependencies orthogonal to the our partial order model. This is where you see that we mention guard variable. This means that under some branches, some events are executed, but under other branches, they are not. This is a representation of data dependency.
More comments on that paper? Okay, maybe later. Thank you. Are the speakers of? Thank you.